Hi everyone, welcome to this Latam High Energy and Mathematics Seminar. Today we are honored to have Professor Cristiane de Morais giving the talk Quantum Fractals from Matter Minors to Real Materials. Cristiane de Morais is a Brazilian theoretical physicist and a professor at the Institute for Theoretical Physics at the University of Utrecht, where she leads a research group studying condensed matter physics, cold atoms, and a strong correlated system. In 2019, the European Physics Society awarded the professor its Emmy Noether distinction. During the seminar, if you have any question, please use raise hand feature on Zoom and I will give you speaking permission. We highly encourage your active participation. Now, I will hand over the conference to the professor and thanks again for accepting our invitation.
My pleasure. Thank you very much. So today I will be telling you about materials for the quantum age and about topological properties at fractal dimensions. So I am a theoretician doing theoretical work, but these three images that you are seeing down here are experimental images, everyone in a very different setup. And I am going to explain you today what they are about and why are they important. Oh, why can't I change my slides? Yeah. So materials. Materials determine the age in which we live, because depending on the materials which are available to us are the devices that we are able to build and the life that we are going to have. So humanity went from the Stone Age to the Bronze Age to the Iron Age, and we are now at the end of the Silicon Age, ready to enter the Quantum Age. To get a perspective, in the 19th and the 20th centuries, we have been dealing more with what I like to call like classical materials, in the sense that we had metals, insulators, and semiconductors at our disposal. And the semiconductors have been extremely important. This is the case of silicon, because they interpolate between a metal and an insulator. So they have a small gap, not large like an insulator, and not a zero gap like a metal. And for this, they could be used to build transistors. And in a transistor, if a current is passing by, this is corresponding to a 1. If there is no current, it's a 0. And we use these ones and zeros to build all the devices that we use, telephones, television, computers, you name it. Okay, so that's then what has characterized the Silicon Age, the use of semiconductors to develop devices, all the ones that we are using now. But then at the, superconductor at the beginning of the 20th century and quantum Hall fluids more at the end, but more exotic materials were discovered in which we could have currents that do not lose energy, dissipationless currents. And now, at the beginning of the 21st century, we already had two very important discoveries, which are graphene and the so-called topological insulators, which actually started at the end of last century with the discovery of quantum Hall fluids. So today I am going to talk about these three topics, starting a little bit with quantum Hall, because this is something you have learned, and going into topological insulators and graphene, and you will see how this relates to fractals, okay? So first of all, I have my, it's not good, I have the things here on top. Do you see the top of my slides?
Yes, it should be topological state of matter.
Okay, very good, because for me they are hidden by the tools that I can touch, but it's good. If you can see it, it's perfect. Okay, so Let's now connect to something you have learned, the quantum Hall effect. So the quantum Hall effect, it was discovered by von Klitzing in 1980 in a material which is not like the one I'm showing here. Here you have a lattice underneath, but it was a continuum. It was a quantum liquid, namely, it was a quantum well of gallium arsenide. Oh, sorry, I'm in the wrong slide. It was a quantum well of gallium arsenide, aluminum gallium arsenide, in which you have a two-dimensional gas of electrons, and you now apply a perpendicular magnetic field. And what happens is that because of the Lorentz force, when you pass a current perpendicular along this plane, you have the magnetic field and the current perpendicular. This will make a Lorentz force in the transverse direction and accumulate charge on one side of your sample, positive charge on one side, negative on the other, and this causes the Hall current, the Hall conductivity. And this Hall conductivity is quantized, and this was the first state of matter, which is insulating in the bulk and conducting at the edge, and it's very important for this reason. And not only that it's insulating and conducting at the same time, but the edge currents, the conductivity is quantized and protected by the topology of the material. It is a dissipationless current that is very robust because it's protected by the topology. So it was a fantastic discovery, but we cannot use this effect that seems so nice because we could have currents that don't lose energy, because this effect only happens at temperatures of about 1 Kelvin in the device that von Klitzing discovered, and it required a very strong magnetic field. So it's not something that we could carry in our pockets. But the effect was discovered, and it was very important. So nearly 25 years later, we already solved one of the problems, because now with the theory, it was a theoretical proposed by Kane and Millet, and they proposed it for graphene, but that was wrong. The idea is that if you now have a material that has a strong spin-orbit coupling, so remember, it couples the spin of the electron that's rotating with its orbital motion. If you would have a material with a strong spin-orbit coupling, this spin-orbit coupling acts as plus magnetic field for spin up and minus magnetic field for spin down. And then you have electrons with the spin up moving in one direction, and the ones with the spin down moving in the opposite direction. The result is that now you don't have a net current because charge moves to the right and to the left, but you have a spin current because the spin up accumulates on one side and the spin down accumulates on the other side. And that was then the so-called quantum spin Hall effect. It is very interesting because the quantum Hall effect breaks time reversal symmetry, because the magnetic field breaks time reversal. If I change T by minus T, when I have put a magnetic field, I have a vector potential. Instead of P squared over 2m for the kinetic energy, I get P minus EA. And P is dx dt. And if I change T by minus T, now because I have this coupling with the gauge field, I have broken time reversal symmetry. It's no longer the same. But here, if I break time reversal symmetry for a spin up, I restore time reversal symmetry for a spin down, because it's like plus magnetic field and minus magnetic field. So these systems preserve time reversal symmetry. The time reversal is invariant. Okay, but as I said, the proposal that they made for graphene, in which now you have these helical spin currents, in which spin up moves in one direction and spin down, which is represented in red, moves in the other direction. it does not occur for graphene. Graphene is a very light element and the spin-orbit coupling is extremely small, so it's impossible to observe. But right after their proposal in 2005, in 2006, Bernevig, Hughes, and Zhang realized that if you would do it for quantum wells again, mercury telluride, cadmium telluride, quantum wells, what would happen is that now you would get band inversion in these quantum wells, and you should be able to see this effect. And indeed, Molenkamp did the experiments immediately in 2006 and has seen this effect. So we have eliminated one of the problematic issues, which was the magnetic field. Now this is an intrinsic property of the material, but still, to observe the effect, he had to go to temperatures of order of 1 Kelvin, which is again a very low temperature, and it does not help us. We cannot carry this device, a device made with this effect, in our pockets, not yet. But at the same time, we had this fantastic discovery of graphene in 2005 that was awarded the Nobel Prize in 2010. And now, in 2007, the group of Novoselov and Geim has put graphene under a strong perpendicular magnetic field. And now they have seen the same quantum Hall effect that von Klitzing needed to go to 1 Kelvin now was manifesting at room temperature. So by going from a quantum well to a solid state material, which has a lattice, we were able to see the same effect at room temperature. And this is a big improvement. But the magnetic field here was still gigantic. It was 29 Tesla. So still, we are not yet there for applications. But now the discovery of graphene has opened the ideas for other kinds of materials that could be also two-dimensional, including the ones which could have a strong spin-orbit coupling. And this was then the case of bismuthine. So bismuth is a heavy atom, and now in 2017, the group of Klassen in Würzburg has realized bismuthine and has shown that for this material, you can observe the quantum spin Hall effect at room temperature. So the dream material has been synthesized, has been discovered, where now we can have a topological insulator, which is insulating in the bulk, conducting at the edge with dissipationless currents at room temperature without the need of using any magnetic field. It is an intrinsic property of the material. So this was really a fantastic discovery. But now we think if we would like to pass over to the engineers this discovery and try to start using these edge currents for making devices with them, we would like to have as many edges as possible, right? Because otherwise, the entire surface of my telephone will have just a tiny edge, and I can't do much with it. I would like to have a surface that has as many edges as possible. And how can I do that? I could make holes inside the sample, but to start making random holes is not really a good idea. The best way would be to make holes in some structured manner. And this means to create a fractal. So what are fractals? Fractals are these very beautiful materials that usually have the property of self-similarity, which means I keep zooming in on them and I keep always seeing the same image. Here you are seeing the Koch curve, which is the structure of ice. And on the side, you have the Mandelbrot set, which is the solution of a mathematical equation. Here, underneath, I am taking another fractal, which is a very easy one, which is the so-called Sierpinski triangle. The Sierpinski triangle is a mathematical fractal. It's an exact fractal that can be built in the following way. Start with a dark triangle. Now you select the middle point of each vertex. You connect these middle points. You have separated your triangle into 4 identical triangles. And now you cut the inner one. The white ones are cut out of the black. You remain now with 3 identical triangles, smaller than the original one. And now we do the same. In each of these smaller black triangles, I will cut a white part, which is the inverted triangle at the center. I will now have 9 smaller triangles, identical to the original one, but just smaller. And in each of these 9, I will again cut an inverted triangle. And each of those processes of cutting, every time I cut, is a generation. So when I have one white big triangle is generation 1. When I have cut the next ones is generation 2, 3, etc. If I go now cutting ad infinitum, I will finish with a structure that will have 0 area, the surface is 0, and the perimeter is infinite. Isn't it odd to have something that has 0 area but infinite perimeter? And the beauty of it is that this structure is not 2-dimensional like the original one that I started with, but it is also not 1-dimensional like a line, but it has a fractal dimension which is between 1 and 2. It has dimension 158. So how does this dimension 158 emerges? The dimension is given by the log of the number divided by the log of the scaling. Which number and which scaling? Let me explain this to you now. Suppose that I have a red line. I am in 1 dimension. I now scale this red line by a factor 2. I get the blue line. This is the factor 2, which is here on the left-hand side. Now I ask you, how many of the red lines I have to put on top of the blue to cover the blue line? The answer is number 2. That is the 2 on the right-hand side of the equal. And this means that the exponent here, which is the dimension, is 1. It's log 2 divided by log 2. This gives me 1. Now let's go to the top of the figure where I have the red square. With this red square, I will now scale it by a factor 2 in the x direction and in the y direction. And I will now get this blue square. So the scaling is 2, again here on the left-hand side of the equality. Now I ask you how many red squares I will need to cover the entire blue square. The number is 4, which means that my exponent here is 2. I am in 2 dimensions because it's log 4 divided by log 2. Okay? And this is 2. So now let's go to the middle here and paint this small triangle completely red. And paint the other bigger triangle completely blue. So now I take the completely red triangle and I scale by 2 here. I double its length here, I double its length here. And I ask you how many of the completely red triangle I need to cover the completely blue triangle. If it would be a completely blue triangle, I would need 4 times the red one because I would be in 2 dimensions. But I have a Sierpinski triangle, so the middle one has been cut. And if I now ask how many I need to cover, it is only 3, because the middle one was cut, and the 3 is what I have now as a number on the right-hand side. And log 3 divided by log 2 is giving me this exponent, which is fractal, which is 1.58. So the dimension of the Sierpinski triangle, the Hausdorff dimension, is 1.58. Okay? And it's something that's not a solid surface in 2D, but not a line, but it's in between. Okay, so why should I care for these odd structures that have non-integer dimensions? The reason is that they are highly related to nature and to humankind. So when I go to walk at the streets and I look at the structure of the trees, I will see that the branches obey a fractal structure, and the roots also have a fractal structure. The fractal structure of the roots is very important to prevent earthquakes. If I go to the supermarket and I buy Romanesco broccoli, again, I see that as I keep zooming in each of these little mountains here, I will always see the same structure. The structure of some leaves is also fractal. And our body is profoundly fractal. Every time that nature needs to change gas carbonic with oxygen or nutrients for the cells, anything that needs to be exchanged, it is very good to do something that's fractal, because you optimize for the same volume, you have much more surface to exchange, which is precisely what we also like to have. So our lungs are fractal, our intestines are fractal, our circulatory system is fractal, our neuronal system are fractals, and even our heartbeat is fractal. But the fractality of the heartbeat is not exact like for the Sierpinski triangle. It is a fractality in a statistical sense. Because if you look now at the heartbeat at 300 minutes, 30 minutes, and 3 minutes, it's not exactly the same. But if you do a statistical analysis of it, it is all the same. And it's profoundly important that the heartbeat is a fractal. Because if it would be chaotic, or if it would be periodic, we would immediately die. It must be a fractal. The fractal is some very subtle equilibrium between order and disorder. And it's very important for humankind. Fractals are also very important for science because, for instance, since they have several length scales that are different, if I would make an antenna with a fractal, I would be able to send and receive short and long length scales at the same time. If I would make a solar cell with a fractal, the largest the complexity of the fractal, the largest is the surface that I can store solar energy. Here you see in blue, this is increasing as I increase the complexity of the fractal. So it's very convenient for optimizing surfaces. But because these fractals are also connected to nature, our senses relate them to beauty. And for this reason, they have been used in arts for very long. This is a Sierpinski triangle used in the floor of a church in Rome from the 1100th century. So Sierpinski was not even born at that time. Nobody knew that this was a fractal, but people were already using it as decoration in churches or in many different places because of their beauty, from their aesthetical appeal. The middle figure here is from Escher. This comes if you project a hyperbolic space into the plane. And now, as you approach the horizon here of this image, you will always see the same structure, but smaller and smaller. And the right-hand side one, this is a painting by Pollock. Pollock was a revolutionary in art. He was putting his canvas on the floor and he was dancing on top of it and pouring colors. But by pouring colors with different density, his work has also a fractal dimension, which has been evolving as he was growing older. So fractals emerge in many different contexts in art. But in science, in the 1980s, there has been lots of activity when Mandelbrot classified and studied a lot the fractals, and the Hausdorff dimension was understood. And many people like Pierre-Gilles Desgènes and Orbach, Alexander, and Kadanoff have studied classical fractals. But now, in our age, we would like to know about quantum fractals. It's time for us to understand quantum fractals. And a first step in this direction was made in 2015 when some chemists have synthesized molecular fractals. So they have been proposing how to use aromatic bromo compounds as building blocks on a silver surface to form things like that. But they have just given us a chemical formula to how to build a fractal at a molecular level. But the question that remained to answer is, if I would have an electron moving in such a structure, would the electron know that it's living at fractal dimension? Or would it think that this is just a two-dimensional system with some holes? Because we cannot go ad infinitum in a physical object. It will, by force, be, we need to cut off the generation. And our fractals are always imperfect in the mathematical sense. They are finite generation fractals. So would a quantum particle, a photon or an electron living in such a structure know that it has fractal dimension? So to answer this kind of question, the easiest way would be to go into quantum simulators. So 160 years ago, Richard Feynman was born, and about 65 years ago, he gave a talk in which he provoked us very much by saying the sentence, "There is plenty of room at the bottom." And with this sentence, he was inviting us to not simply, we physicists, to not simply explain matter, but take matter in our hands and construct matter in a bottom-up approach with the properties that we would like to have. And this is what is going to be required for the new age that we are entering, for the quantum age. We are going to build materials, to manipulate materials, and to design them according to our needs to perform the function that we wish in the most energy-saving manner that we are able to design. So when he told his ideas, people took many, many years to start understanding the depth and the importance of what he was saying. And it's nearly 30 years ago when the first cold atom quantum simulators has been realized with optical lattices to simulate the Bose-Hubbard model. After that, we had some photonic quantum simulators using photons, and only more recently, electronic quantum simulators. So I will tell you a little bit about the first and the second today, and the third, I will just tell you at the very end, an experiment that we are trying to do with that. Okay? So I will start with the electronic quantum simulator because this is the least known. You very seldom hear talks about that. So what are we going to build to be an electronic quantum simulator? We are going to do the following. We will take a metal like copper and take its surface state at the surface 111. It turns out that metals above a certain threshold of energy, they will have a gas of electrons floating on their surface, a metallic liquid of electrons. And that's what we want to use for our quantum simulator. And in addition to that, we are going to use something called adsorbates, and these are going to be carbon monoxide adsorbates, hundreds of them. They are like little mountains that we are going to put on top of the atoms one by one. And this manipulation is going to be done with what is called an STM, a scanning tunneling microscope. Okay? So the scanning tunneling microscope is usually used to see the structure of materials with atomic resolution or to measure, to do spectroscopy. But here we are going to use it also as a third function, to use it as a needle that can move this carbon monoxide one by one to position them where we want. So this idea is based on the pioneering work done in the group of Don Eigler in Caltech in 1993. So what Don Eigler did, he took the surface of copper, 111, and he patterned atoms of iron. So each spike that you are seeing here in red is one atom of iron, which is now making a circle here on top of the surface of copper. And the separation between two spikes is 1.1 nanometers. So it's patterned on an extremely small length scale. And what you are seeing here inside, these blue waves, are the wave function of the electrons. So they called this a quantum chorale because in the same way how the chorales are going to make waves in the sea, here you get these atoms of iron closing my electronic wave functions, which are going to make waves in a quantum chorale. So this was an extremely beautiful experiment that allowed us to visualize something as small as a wave function of an electron. And to make publicity for their work, they made this movie that you are seeing here on the right. It's called A Boy and His Atom. And this is the smallest video ever made. So IBM was making the publicity for that. Each pixel in this movie is one atom. Okay, so the atoms are being patterned one by one on top of a surface. And if you want to see more of the movie, you can find it on YouTube. Okay, so, but this was in 93, and it took, again, almost 20 years for people to realize that we could put these quantum chorales together and control. You see now here, this black are the confining mountains that I'm putting around my two-dimensional electron gas. And the blue sites are the sites where the electrons are going to sit. I can control the door. I can open the door like in G a little bit, or I can open the door further like in E. And by tuning now how open is the connection between the two blue sites, I will open the tunneling. This will make electrons tunnel from one blue site to another. And in the spectrum of energy, I will split the energy values, depending by an amount that depends on how large is the tunneling. So we can manipulate the band structure of these materials. And after that, this idea came from the group of Hari Manoharan in Stanford, and he used this idea to connect these quantum wells to build what he called molecular graphene. So what you are seeing here in yellow are the electrons moving on top of copper 111. And then he is putting many adsorbates. These are the brown mountains that you are seeing here, completely disordered. So when you irradiate, you will get all these disordered COs, carbon monoxide. And now he will come with the tip of the STM, pick the COs one by one and push them in the right position to pattern a triangular lattice with them. But as you pattern a triangular lattice with these mountains, the liquid of electrons has to go around, and then the liquid of electrons has to form a honeycomb, a hexagon. And indeed, they are forming an artificial graphene lattice because graphene has this hexagonal lattice. The only difference is that you see here underneath this graphene lattice, you see 2 nanometers. In graphene, this lattice would be formed on the length scale of angstroms, 10 times smaller. So we have been building graphene 10 times larger by an artificial means, and it's perfect. The lattice is absolutely perfect. And if I make a mistake, I can immediately know. So this discovery has been extremely important because it has opened us a way to perform electronic quantum simulators. But this type of experiment had a problem because I can only put the COs on top of copper, and the underlying lattice of copper is triangular. So the first question was then, can I only pattern triangular lattices or honeycomb lattices on top of that? Lattices which are consistent with the threefold symmetry, or should I be able to pattern a square lattice, like different square lattices that I could imagine? So, and the second thing is, it's not obvious that I would be able to pattern a square lattice because the ones that I am patterning the anti-lattice, and this one needs to have that here happen to have the same symmetry as copper, but we'll find a way to build more general lattices. So this is when we entered the field in collaboration with my experimental colleagues at Utrecht University, Ingmar Zwart, who is a specialist in STM, and Danielle van Mackelberg. We have done a series of works in which we simulated different lattices. We constructed something which is called a Lib lattice, which is like a square, but you take away the central point. So you get a lattice with 3 sites per unit cell. Then we have been showing how to control orbital degrees of freedom, like S, Px, and Py, in this lattice under demand, and split the orbital, for instance, Px and Py, degeneracy, by finding how to break the right symmetries that make them degenerate. That was published here in 2019. Then we went on and we discovered how to have flat p-bands in these materials if instead of doing what Manoharan did, that was to put just one CO here in the middle of each hexagon, we were then putting a rosette of COs, a circle of COs and another circle to increase quantum confinement and modify the band structure. And then we could get a flat p-band. And after that, we went into studying topology in Akekule lattice, how to get corner modes in a Kagome lattice. Those ones were published in 2020 and 2019. And more recently, we realized something different, which is called a diamond necklace. And for this one-dimensional chain, I was able to get, we did, because it's a work that we did all together, we were able to get end states here, this yellow that you are seeing in the experiments, which do not decay exponentially. All the topological states that you know, they decay exponentially into the bulk, but those they don't. They are compact localized states on one side. You can read more about it in our paper in Quantum Frontiers if you wish. So, but today, the things that I want to talk to you about are electronic quantum simulators and the quantum fractal, because we went on to build the first quantum fractal for electrons. This work was published in 2019, and we were very proud when it was selected as one of the 15 highlights to celebrate the 15th anniversary of nature physics in 2020. So after that, all the setups that are made with electrons, they are not prone for probing dynamics. So in collaboration with a Chinese group in Shanghai Jiao Tong University, we went on to study the dynamics in a quantum fractal. And now, currently, we are trying to build a quantum simulator using cold atoms. I will mention it at the end. But after telling you the details about the photonic quantum simulators in the second hour, I will tell you now about topological effects in fractals. We were able to get the first emergent fractal in a real material, because the previous ones were all quantum simulators. This work is going to appear in Nature Physics on Monday, coming Monday, and there will also be a publicity for it in this community website from Nature Physics, where you can read in more simple terms our description of the work. So today I want to tell you about that. And let me then start with our work. Do you have questions until now? Let me wait a little bit.
I don't see questions.
No? Is it clear? Is the level okay?
I think so.
Okay.
I think it's proper for our audience.
Okay, very good. So let's then continue and ask ourselves now, how do electrons behave in fractional dimensions? And you will tell me what the frac. This work was done by Sander Kempkes, who was my PhD student. He calculated where should we put the COs to see the effects, and Marlouis Lott was the one doing the experiments in the group of Ingmar Zwart and Daniel van Meckelberg. Okay, so we are going to build Sierpinski fractals of first, second, and third generation. And for this, we are going to use the setups that you can see here on the right-hand side. We are putting these mountains of carbon monoxide, the black dots, to confine the structure, one in the center for the first generation, or 4 in the center and 2 in the little ones for the second generation, and this one for the third generation. And if you look here on the left-hand side in B, for the first generation, we imagine that for this configuration, there will be atomic sites at the red, blue, and green sites where the electrons can sit. And now they will hop between these sites. And we are designing them by different colors because the red sites have only one neighbor. The blue sites have 3 neighbors and the green sites have 2 neighbors, okay? So then we will first do a kind of a calculation that's called a muffin tin model. And this is a very easy calculation. You see, this is a tin to bake muffin. I put it upside down and I have my electrons moving in between. Here, they would be forming a square lattice. So their effective mass is, we know, is 0.38 times the electron mass. We know the height of these barriers and we know the diameter of the barriers. The radius is 0.6 nanometer. So we can simply solve Schrödinger equation for a fractal configuration and understand how are the energies and the local density of states, which is nothing but the wave function of the electrons modulus square. And after that, we can also describe this by hopping on a lattice, which is a kind of a tight binding approach. We will then come and take this sample and measure now the GI/GV curves at many red points, at many blue points and many green points, take their average and get this GI/GV spectrum versus voltage, okay? And you will see features like this. There are points when energies, like at minus 300 MeV, when everybody has the same energy, the red, the green, and the blue sides. But there are points where the green and the blue are high and the red is low, like at minus 200, or when the red and green are high and the blue is low, like minus 100 electron volts. So we can calculate this from our simplified model, and we see that we can capture the main features that are being seen in the experiments. So now what we do is we say, okay, now let's sit at each of these energies, minus 300, minus 200, and minus 100, and scan the entire sample to look at the local density of states, the map. And then what you see here on the top is what you obtain experimentally. The first vertical is minus 300 MeV, the second is minus 200, the third is minus 100, and the bottom is the theoretical calculations. So first of all, you see that the theoretical calculations agree very well with the experiments. On the left, we are seeing the bonding configuration, which looks pretty much like a Sierpinski. On the complete right, we have the anti-bonding configuration, and in the middle, we have the non-bonding configuration. So it looks like our electrons are forming a fractal, a Sierpinski triangle. So now the big question, do they see that they live in fractal dimension, or do they think that they are living in 2 dimensions? So in order to answer this question, we have to perform something that's called a box counting or Minkowski-Bulligand method and measure all these white parts that I am now binarizing that are actually the peaks that we were seeing before. I now binarize these peaks in white and black, and I cover all the white parts by a square, or it could be also a circle, of a dimension that is reasonable compared to the size of the object I want to cover. So I select a certain size, and I cover as well as I can with as many as I need. And then I count how many of those I need, 1, 2, 3, 4, 5. And then I'm going to plot the log of the number versus the log of the inverse radius of this pink circle. And I will find a point, which is the pink point here. Now, instead of using this circle, I use a smaller circle. I cover everything again. I will have a different number of circles that I need to cover the structure. And I come back to my log plot, and I have another point. And I keep decreasing the size of my holes, of my circles, and increasing the size. And every time I cover everything and I count. And every time I get a point here. And after doing this tedious exercise many times, I will realize that all these dots are sitting on a straight line. And this straight line is the dimension of the object that I am covering in pink. So the dimension of the electronic wave function that I am covering here for the -300 MeV is 1.59. And remember that the perfect triangle had a dimension 158. So the electronic wave function is seeing that the electrons are living in fractal dimension. You can do the same exercise that we did for -300 for all the other energies, and you will get all these points that you are seeing here. If I would have been doing this for the square lattice, I would get the green points, which is 2. But the red points, you can see they are around 1.6, which is the dimension of the Sierpinski triangle. You are seeing here that we have some error bars. You see the biggest error bars appear at -100 millielectron volts, which are for this structure. This does not look much like a fractal, right? And the error bars come because I told you I am binarizing this structure in black and white. While I am covering, you see there is some gray here. And is the gray white or is the gray black? You have to use some ad hoc procedure for that. So we said that all peaks which are up to 75% of the highest peak are white. Everything what's below that is black. And those are the dots that you are seeing here. But we could have said all the peaks which are up to 60% of the highest peak, or which are up to 90% of the highest peak. And these are the boundaries of the error bars that you are seeing here. It gives us a feeling that no matter what we select as the criterion to binarize this structure, we are always around 1.6. So it makes us be confident to say that the electrons know that they are living in fractal dimension. Okay, so that's then the conclusion from this work. Okay, we were patterning CO on copper 111 in the nanometer range, and we have shown that the electronic wave function fills the fractal dimension. Good. So any question about this work until now?
There's a question in the chat box.
Yes, let me see, there are 2. Now, how come that there is such a bit between the original article here? Which big difference? Maybe you can ask loud, the person who is asking this question. Luco? Maybe you can explain your question. There is an erratum for the paper in 2020, but when you click on the paper, you will immediately be directed to the erratum. There is no big difference. The question is that the method, let me get back to the slides, wait a minute. This Minkowski-Bulligand method is an approximate method, okay? And depending on where you start and where you go, you could have different slopes here. And when we wrote the erratum, we really investigate and we were playing devil's advocate for the worst possible scenario for getting these dots here. And so the work that was published in the erratum is done with an enormous care in analyzing all the drawbacks of the method to make sure that there is no way you could, there is no way that if you would take the worst possible scenario for that method, that's what I am showing you here. Okay? Is there any other question? Okay, then I close the chat and we continue for the dynamical part now. So that is now the work for another quantum simulator on a photonic setup. And if we would like to study dynamics, we cannot use STM because STM is a static technique. Then we need to use some other setup. And in 2019, I was in Shanghai visiting the group of Professor Shan Mingjing, and I have seen the measurements that they were doing on fractals, and I started collaborating with them, and we could then understand how is the quantum dynamics in a fractal. So when Dejean was studying the dynamics of classical particles in fractals, he used to say that this is the problem of an ant in a labyrinth. So I like to say that this is a quantum ant in a labyrinth. How would a quantum ant behave if I put them to move in a labyrinth? And the paper was published in 2021. Okay, so let me tell you what we are going to build. We are going to use a method that is called femtosecond laser direct writing techniques. You shine a laser on a chip, and at a certain depth, it will make a line inside your chip. And these lines are these pink lines that you are seeing here, which have a transverse section, which is the black dot that you are seeing here. And you will make these lines in different depths such that the cross-section will have the shape of a Sierpinski triangle, okay? So each of these pink lines is a waveguide, and you will inject a photon at the top of this setup, and the photon will move along the waveguide. But the length of this waveguide is going to play the role of time for us, which means when you inject a particle here, it will propagate along this pink line with the speed of light. And when it comes to the end, you detect it, okay? And this means the length divided by the speed of light gives me time. Because I would like to have a quasi-continuous time, we will make hundreds of these setups where this length in the pink direction is different, a short, slightly longer, slightly longer, slightly longer, because this is what is discretizing my time. And at the same time that these electrons will move along the waveguide with the speed of light, they will hop from one waveguide to the next by quantum tunneling, as electrons do in a lattice, okay? And it's this hopping procedure that is going to be described by a tight binding on a fractal. It's what we are going to use to see how a quantum particle, a photon, is going to move in a fractal. So this technique is called continuous time quantum walk, okay? So we are going to analyze, in addition to the Sierpinski triangle that has dimension 158, we are going to investigate a Sierpinski carpet, which has dimension 1.89. This is because if I take here this left triangle and I scale it by 3 in the x and by 3 in the y direction, I am going to get 8 copies because the central one is gone. And log 8 divided by log 3 gives me 189. In addition to this structure is called the Sierpinski carpet, in opposition to the Sierpinski triangle. And now I can also build something which is called a dual Sierpinski carpet, in which I take the each square that is filled here in the Sierpinski carpet, and to the center of a filled square, I will put a dot. And if I do this, I will build this structure down here, which is called a dual Sierpinski carpet, okay? The dual Sierpinski carpet has the same fractal dimension as the Sierpinski carpet, but the distribution of holes is different. You see here, I start with a hole from the very beginning when I inject a photon at the corner, whereas here I have many waveguides before it meets the first hole. So we are then going to investigate these three different fractals to understand what is the role of the fractal dimension and of the distribution of voids. So these are then the results for the Sierpinski gasket. What is happening is that every time when they take one time here, so I am plotting here on the right-hand side, the variance, the mean square displacement, as a function of the propagation length, which is some on the z direction, on the pink direction, which is like time, okay? If I would have normal diffusion of a normal particle, I would expect that the variance would scale with the length square or the time square, which is ballistic behavior in the beginning. And if it becomes diffusive, as for a Langevin equation for a particle into a viscous medium, this would become proportional to time, linearly proportional to time. It goes from t squared to t. But here, what is playing the role of time is z, this length scale. It is starting with 2.5, and then it's becoming 1.58, and then it's saturating. Let's see if we can understand what's happening here by taking images of the photons in the transverse direction, in this cross section, every time when I detect a photon at the end of the waveguide. Okay? So what you see is this interference pattern that we are seeing here on the left. Basically, it's the following. I take now 3 snapshots at 3 special points where these things are changing. First, I see that this exponent is 2.5 instead of 2. The reason for that is because we are injecting at the corner of a triangle. If I would have a filled triangle and I would inject in the center of the filled triangle, such that my particle could move in the 360 degrees around, I would then have an exponent 2. But because of the confinement of the edge, it cannot go around, I find that is 2.5, okay? And then I see that when here at this point, which is 2.675, that has this dashed line, this red curve started deviating from 2.5. And when it's precisely at 3.875, which is the point, so 2.675 is the point when the photons have met the first hole. And 3.875 is when the photons went around and could again go on propagating. And after meeting the first hole, at the point when they can propagate again, they pick up the fractal dimension. It is absolutely curious that by seeing one hole, they already understand the fractal dimension, which is a property of the entire system. And finally, when I have explored the entire sample, my mean square displacement saturates because particles start coming back, okay? And if we do a quantum simulation for what you would expect numerically, you see precisely the same features as seen in the experiment. But what is very important here is that this mean square displacement is scaling just with the fractal dimension, and this is different from the classical case where it scales with the spectral dimension divided by the Hausdorff dimension. Here is just the Hausdorff dimension that's appearing. So this is telling me that the quantum diffusion in a fractal is different than the classical diffusion in a fractal. I can distinguish the two things. And now we look also at something called the Polya number, which is related to the return probability. It's not very essential, and because the time is going fast, I will just tell you very fast here that by measuring the Polya number, you see that you have a plateau when you reach the point that the system is entering into the fractal regime. Then we repeated the same experiment to see whether that exponent 158 was by chance. We do it now for the Sierpinski carpet. And now I see precisely the same feature. It now starts with 2.4, the exponent, because now I have a square instead of a triangle. So the regime along which I can diffuse is larger. And this exponent is now 2.4. And when I meet the first hole, it starts deviating from 2.4. And it's here, 3.85. And at 5.95, the photons went around the first hole, and they can again propagate, and they exactly pick up the 1.89. You can see the same in the numerical simulations. You see here there is a little difference. This is real world. This is an experiment. And if they do not inject things, these are very small waveguides. And if they do not inject the photon really perpendicular to the walls of the waveguide, what happens is that it bounces and you see little errors in the measurements. But this is very normal in an experimental world. And we then confirm that from the moment when the photons meet the first hole, they start diffusing with the fractal dimension. Now, when we repeat the experiments for the Sierpinski carpet, we see now it starts directly with 189, as it should, because it's meeting a hole from the very beginning. So our expectations are confirmed. Now, I used this quantum simulator to make some analogies with a problem that we had that was going on, and it is still going on, which is the issue of consciousness. So many years ago, like 35 years ago, Roger Penrose, that you might know because he got the Nobel Prize for quantum holes, for black holes, he was proposing that the processes in the brain should be quantum. He was working together with Stuart Hameroff, who is an anesthesiologist, and they thought that our brain, the information in the brain would be usually in a superposition of different states, and it would propagate according to the laws of quantum mechanics. But because this state is very fragile, from time to time, this would collapse due to fluctuations. And when it collapses, we are conscious of something. And when our brain is in a superposition, we are not conscious. So in this way, if you don't know if you have closed the door of your apartment, your brain was in a superposition between open and closed, but in the moment when you collapse your wave function, you are aware that you have closed. So at the time, you can imagine people didn't like the idea because you would only observe quantum features at very low temperatures, like 1 Kelvin. Remember in 1980, to see the quantum Hall effect, von Klitzing needed to go to 1 Kelvin. And people would say, but the brain is functioning at room temperature. How can you have quantum coherence and get quantum effects at room temperature? So now I have just told you that for graphene, the quantum Hall effect has been observed by the group of Andregeim at room temperature. But you will tell me, okay, but they needed a 29 Tesla. I don't have a 29 Tesla in my brain. Well, maybe we do. Maybe we do even more. Because when graphene was discovered, people, Cromie, did some experiments when he was gluing graphene on top of the substrate. There are always bubbles that are formed. It's very difficult to glue a thin membrane on top of another membrane. And what happens is that these bubbles, they generate, because of their curvature, they generate pseudomagnetic fields of 300 Tesla, 400 Tesla. He could measure that. So we could have curvature generating enormous magnetic fields. And in addition to that, the neurons, they are made of carbon nanotubes. And we know that carbon is very light. It cannot realize the quantum spin Hall effect predicted by Ken and Millet, precisely because carbon is very light. But if you fold carbon to build a carbon nanotube, the folding increases the spin orbit coupling. This has been measured in Delft by the group of Leo Kalvenhoven. So then you could have a strong spin orbit coupling. So by now, with all these last experiments that appeared in the last year, I do not contest at all that processes in the brain could be quantum. And on top of it, topology could be very important. They didn't talk about topology. And what our work did, our work has been making a very clear prediction about how the exponent should be for a quantum diffusion. So if the biologists are able to measure the diffusion in the brain, they can immediately check whether it agrees with the classical or with the quantum prediction. And then we can know without any fight whether these processes are classical or quantum. So there was this interview that I gave in the conversation, and if you want to see, you can check there, where I explained then why our research takes a step closer to find out whether consciousness could be explained by quantum physics. Very good. So now I would like to make the break. It's 1 hour. We could make a 10 minutes break before starting about topology. But before that, I want to know whether there are any questions. No? Okay, then I propose that we make a break and we come back at 27. Okay, very good. So now in the second part of this lecture, we will ask ourselves, what about topology? So topology is, as you know, has been started with the quantum Hall effect. It went on with the quantum spin Hall effect. And in the meantime, it has been classified in a bird view, the types of topology that we can have, depending on the symmetry class, depending if we have time reversal, charge, electron hole conjugation, and sublattice symmetry, chiral symmetry or not, and depending on the dimensionality. For the case of non-interacting systems, we perfectly know to which class they belong, and just by looking at the symmetries and the dimensionality, you can immediately know if it is going to be something like the quantum Hall effect, which is class Z, where you can have an integer number of edge states, 1, 2, 3, 4, 5, or if it could be something of class Z2, as we have for the Kane-Millet model in 2 dimensions, for instance. And for no-interacting systems, we know what to expect. You have learned how to calculate Chern numbers, and everything is fine. But now the question is, how do you transition from 1 to 2D? If you take a certain symmetry class, like quantum Hall, that has no symmetries, and you are in 2 dimensions, you have topology, in 1 dimension you don't. When do you lose it? Is it at 1.9? or is it at 1.1? What happens in between? Do we have one of those or none of those or something else? How much could topology survive when I start changing the dimension, even for non-interacting systems? And that's then the question that I would like to answer. So if we look at topological studies in fractals, there have been lots of experiments. There is lots of theory. I didn't make a slide for you. And ourselves, we did also many works there that are works by the group of Katz-Nelson, by the group of Zurich, Mana and Bittenroy. There are many, many groups studying, doing theory on these systems. In some experiments, but the experiments are all metamaterials, artificial materials, like in photonics, they do a helical, this waveguide that I was telling you straight, you can now rotate it, and this simulates the quantum Hall effect or the anomalous quantum Hall. So people did photonic Floquet, fractal photonic TIs also here, and anomalous Floquet. So there has been a series of experiments in photonic systems. Also acoustic systems, especially in China. These are these two groups, very beautiful experiments. These are acoustic metamaterials which simulate a topological system, but they are all metamaterials. And then the question is, what about a real material? Do we have any hope to find a fractal which is topological in a real material? Well, you remember that I told you about the group of Klassen who could measure a quantum spin Hall effect in bismuthine at room temperature. So the group of Jinfeng Jia in Shanghai, Jiaotong University, here is Shen Liu. She was doing these experiments, and she was growing bismuth on top of indium antimonide. And she realized that if she varies the time that she lets the material depositing, the time that she raises the temperature and anneals and does this and that, she could get the formation of these fractals. Okay, so at the first work, they thought that they were not topological, but then based on some calculations, but then we studied it very much in depth, and we understood everything now, I think, even quantitatively, which is being seen in those experiments. So this paper is going to appear on Monday, 1st of July, in Nature Physics, and you can also read a bit about it in this publicity from Nature Physics, that there is a simple explanation about, for the public in general, about what we are doing there. So here you can see a big piece of the sample. In brown, you see indium antimonide, and then you see a single layer of bismuth forming this Sierpinski triangle. And the number 2 means that you have another film on top. And sometimes you even form another single layer bismuth fractal on top of the films, which is a second layer. So you can do a very in-depth study of the layers and see them one by one. You can see things with atomic precision. And you know, because you do spectroscopy, and you know that your substrate and your wetting layer, this is the 0 here, have a gap around the 0 energy, 0 bias. And now you start doing spectroscopy along this edge, and you do along at all those points which are indicated here. And when you are at the corners, you see here the appearance of a peak at 0 bias energy. And this is going to be, this was for us, first of all, a sign that there should be some topology going on there, especially because we know that bismuth single layer has a gap, a spin orbit coupling very strong that leads to gap of the order of room temperature. So this was smelling like a corner mode. And then we went on to investigating this theoretically. So this was the work of Robert Canelas. It was his master thesis, and Rodrigo Arouca was also co-supervising his work, was the daily supervisor. And basically what we have to do now is to take our previous Schrödinger equation and add the spin-orbit coupling to this continuum description, because if there is a strong spin-orbit coupling in bismuthine, this term is going to be very important. You are seeing here a third generation with all the different neighbors that is going to be taken into account. So now I try to show you some of the highlights of the work to just understand the main features. If you would like to see more details, you should go to the supplementary information, which is very long and show all the details. So you see here theoretical results plotted in a pink column, in a purple column, and in a green column. Each column has different ingredients in the equation. This pink column has only kinetic energy. So it's the same as we had before with the electronic quantum simulator. The purple, we are including intrinsic spin-orbit coupling. And this is the main element in the model by Kane and Meillet that should generate topological effects like the quantum spin Hall effect. And now in the green, in addition to the intrinsic spin-orbit coupling, we are including also the Rashba spin-orbit coupling. But the Rashba spin-orbit coupling breaks time reversal symmetry. The Rashba spin-orbit coupling makes a mess there, because if you have only intrinsic spin-orbit coupling, this means hopping to next nearest neighbors and keeping the spin as a good quantum number. But the Rashba will be hopping between nearest neighbors by flipping the spin. So now you have to take both spins into account. It makes our life much more complicated, and it closes the gap that had been opened by the intrinsic spin-orbit coupling that was producing the topology and destroys the topology. So this is known to occur for the graphene sample in the framework of the Kane and Meillet model. So here, what we'll see, we look first at the local density of states, and then we select some interesting energies at which you see peaks or dips, and we do the map scanning the local density of states in the entire sample at that particular energy. You see here 4 selected energies as we had before. Before we had 3 here, you see 1 more. So now we see what changes when we put the intrinsic spin-orbit coupling. And basically what changes is that before the red and the green, and remember the red is the corner and the green is the edge. Blue is the bulk, the black and the blue here. So where I had before a peak for the red and for the green, now I have a peak for the red, but a dip for the green. And this is what is going to allow me to see here these corner modes that you are seeing in the second slide in the purple column. These are topological corner modes in my sample at 0 energy. Those were the spikes that you are seeing in the experiment. And in addition to that, at higher energies, I can see also edge states running completely around the big triangle or also around the smaller triangle in the center. And if I now add a Rashba spin-orbit coupling, it kills completely all the effects. So this is then the signature that these effects are topological, generated by the intrinsic spin-orbit coupling, as in the case of Kane-Meillet, because they are then destroyed by Rashba. In addition to that, if those are topological effects, they should be resilient to disorder. So let me show you now, before talking about the disorder, let me first show you what the experiments are doing. They are scanning the entire triangle at various different values of energy. You see here it's starting at minus 507, minus 266, minus 104, 16, 97, 238, 108, 318, and 459. So, and in a long range of energies, you would see the same features. It's not a feature that you see at one specific energy, but you see for a very broad range of energies. And this is the same for our calculations that you are seeing here, the scans, the maps, at comparable energies. So for negative energies, you would see a bulk state. Pink means very high. The modulus of psi squared is very high. There is a peak. And cyan, blue, means it's very low. So at negative, very deep negative bias voltages, in minus 500, minus 200, and so, you see that all the intensity is in the bulk, and you see the cyan line around it. I will talk about it later. You see also in the experiments, this blue line around. And then when it comes around 104, here it seems to be 4 blobs. And here we find 5 dots. This one is not very much in agreement yet. Then when it comes around 0 energy, here is 16, here is 31, you see these corner states emerging. They stay around 0 in a broad range. Then as you approach 100 MeV, you see the outer edge states. They are in a triangle looking up. And around 200, you see the inner edge state. It's a triangle looking down now. You see here the theory and experiments. And at higher energies, it becomes a kind of a mess because you have higher orbitals. But you still can see features which are similar. But you see, we still didn't have here a complete quantitative agreement with the energies where you are seeing the phases. And this one was not identical to what we were predicting by the theory. Then we decided to go on studying effects of disorder because you know that this triangle is not perfect, the Sierpinski triangle. Disorder is very important in real materials, much more than in metamaterials. So we have been studying 3 different types of disorder. This first line, you see here that we are creating Sierpinskis, which are a mass, combining pieces of Sierpinskis with each other. And as you can see, these corner states still appear. And the edge states, we are looking at the first line. I don't know if you can see my cursor. And the edge states too, in the outer and in the inner edges. Now, if we put disorder in the height of the barriers which are confining the geometry of the Sierpinski, again, you see, we go from the bulk phase to the corner phase and to the edge phases. The difference is that now, for instance, this tiny circulation in the little edge now appears at the same time as the outer edge, because if you have locally a different disorder, a different potential, the energy would appear, the edge state would appear at a different energy. So you see some coexistence of phases that you wouldn't see in the clean material, but the phases themselves are robust, signaling that they are topological. And you must consider that we are making the material really amorphous. We are going to 40, 50, 60% of disorder. It's gigantic, and the features persist. And in this last one, we changed the position of the pixels in the fractal lattice. This one is the most detrimental one, but still, you will still see, you see the bulk, you see the corners, and you see the edge. So again, the phases are robust. But then we go on and we put a different type of disorder. We tilt the sample inside the boundaries, because there is also destructive interference with the boundaries of the sample or what is around. And instead of considering these atomically resolved sites, we take a sharp, straight edge. And when we do this, then we get an incredible agreement with what is being seen experimentally, because now you see the energies agree in the range where they are being seen, and these four blobs, now we see the four blobs here. This is the bulk phase with this very sharp blue around. And here we had the corner mode, but we were unable to see the third one in the experiments. And when we, in the theory, we had all the three, but now when you tilt the sample, this one disappears due to destructive interference. And you also understand for this outer edge mode why the lower one is less prominent than the other ones. Again, it's the same destructive interference that is vanishing with this corner mode. So now, after taking disorder into account, we had a quantitative agreement with the experiments, and we could confirm the realization of the first topological quantum spin Hall state in a fractal that is emergent in a real material. It's not a metal material, okay? And this then gives us hope that we could, in future, build devices which could have lots of edges and lots of running currents, which are protected. This would be, it's a very first step, what we are making now, but it tells us there could be this possibility. Here is just another detail for showing this very sharp edge. This very sharp blue edge, this is a depleted state that appears at negative energies. This is a very curious feature. We see the same in the calculations, but we don't know what's the reason for it to appear. It's something that remains to be elucidated. Now, I have still like 15 minutes. So I will tell you a little bit about effect of interactions at fractional dimensions. But before I change topic, are there questions about this topic, the topology? Anyone wants to ask anything? I don't see. Oh, why can't I go? Ah, here. Good. Nothing in the chat. Good. So then I will continue. And let's look at the effect of interactions at fractional dimension. So the behavior of electrons depends enormously on the dimensionality. We know that electrons always interact via Coulomb interactions, but if they are in 3 dimensions, because of screening, the Landau Fermi liquid theory tells us that we can treat electrons as non-interacting, given that we replace the electron mass by the band mass in the material, in the solid. So it's just a quasi-particle with a renormalized mass, and they behave as non-interacting. In 2 dimensions, as we reduce the dimensionality, quantum effects become more prominent and interactions become more important. In 2 dimensions, you have learned that if you apply a perpendicular magnetic field to your electrons and go into fractional filling of your Landau levels, you can have the fractional quantum Hall effect where we get charge fractionalization. So the excitations are quasi-particles with a fraction of the electron charge, which is a very interesting state, but only appears at 2D. Now, in 1 dimensions, interactions are extremely important, and they give rise to what's called the Luttinger liquid. And here we can have a different kind of fractionalization in a way, because they spin and the charge excitations move with different velocities and they separate. So we get a phenomenon that's called the spin charge separation in 1 dimensions. So we can see that interactions can bring very rich behavior depending on the dimensionality. And the question then is, what would interactions do at fractal dimensions, for instance, at 1.58. So we went on last year investigating the fractal lattice Hubbard model. That was the master thesis of Monica Conte. And what you see here is that you build the fractal in this way. You put your sites at the vertices and at the filled triangles. So this is like a honeycomb flake where you have here one missing site, okay? And this is the second generation of the Sierpinski triangle. But when you have a sample like this, we will now call it two sublattices. The black ones, which have 3 neighbors, and all the others that have 1 neighbor or 2 neighbors, I will paint them in white. And then, in analogy with graphene, I can see that I have a lattice with AB sublattices, but differently from graphene, because now I have a finite size system, it's a flake, and in addition, I have one missing atom here in the center. I have sites with different connectivity. I have sites with 2 and sites with 3 neighbors because of the finite size of my flake. I have a lattice with a different number of A and B sites. For instance, there are 15 white circles and only 9 black circles here. So this makes the same kind of physics that we studied in lattices, which have the same connectivity. All sites have same connectivity, and you have equal number of sublattices. It brings a complete novelty to the problem, okay? And now we analyze the Hubbard model on this fractal using quantum Monte Carlo exact diagonalization and mean field. And when we do this, what you find is something very interesting. We find a phase which is going to be ferrimagnetic, and ferrimagnetic means it's like an anti-ferromagnetic phase where you have spin up, spin down, spin up, spin down, alternating, but the intensity of this blue arrow is smaller than the red one. That's what makes it a ferrimagnetic metallic phase, because the total magnetization is not 0, but it's positive. It will be the difference between the red and the blue. But what is very interesting here is that when you try to understand what kind of state is this state is metallic. And it's the first time that a state that is metallic and magnetic has been found in a Hubbard model. Hubbard himself was desperately looking for different lattices where he could find a state that's metallic and magnetic. But all the time, either they are magnetic and insulating, or they are paramagnetic and metallic. He couldn't combine the two. But at the moment when we take a lattice that is on a fractal and has all these particularities with different number of connectivities and different numbers of AB sublattices, this type of state emerges. And curiously, the transition from the insulating to the metallic phase happens at the same critical value of the parameter U as for the honeycomb, but it's now a transition between different phases than you have for the honeycomb. So now I will just make a publicity for another work that we also did. We have been trying to create fractal nodal band structures. So if you have now systems which are non-Hermitian, they are described by a Hamiltonian where H is different from H daga, you can have nodal points at node points which are going to have 0 energy. And these nodal points form Fermi surface. And what we found is that it's possible to create models such that in K space, we would have a fractal Fermi surface. And what you are seeing here, this contour of these images, is the fractal Fermi surface. And here again is the contour of the blue parts, which are my fractal Fermi surfaces. And then you could think that phenomena like charge density wave, where you have nesting at the Fermi surface vectors, or superconductivity, where you make Cooper pairs at the Fermi surface parts, could now become fractal. It could be extremely interesting if one could realize this in real life. Finally, I show you one slide about an experiment that's going on with cold atoms. This is an experiment done in Amsterdam in the group of Florian Schreck. And they are using optical tweezers to trap atoms, strontium atoms. These are Rydberg atoms. They have a very long range interaction. And they, instead of having a square lattice like you see here in this purple sites where the atoms are sitting, they are forming a fractal lattice. And then this model is like the Ising model in a transverse field in a fractal lattice. And we are devising new numerical methods to handle that. Okay, so this is a work in progress. It will still take a while. And with this, I want to finish, but before I finish, I want to show you a little game. So our friend Einstein has been telling us that God does not play dice with the universe. Now I want to play dice with you. We are going to do the following. It's called quantum chaos game. Let me just show a little bit, and then I stop. So we are going to draw a triangle, and now we are going to choose a random point inside the triangle. Now we are going to number the corners of the triangle like 1, 2, 3. But because I only have dice with 6 numbers, we say 1, 2, 3, 4, 5, 6. Okay? And now, after we have selected this central point, after we have selected the central point, let me play. You pick the random point and you play the dice. And you get, let's say, number 2. You connect the point to the vertex 2 and you select the middle point. Play dice again. You got number 1, connect to vertex 1 and choose middle point. Got again number 2. And you go on playing. And you play dice 100 times. And every time you get a number, you connect your point to that vertex and choose the middle point. And after 1,000 iterations, you have got a fractal emerging from a completely random game. So maybe God plays dice with the universe because we have lots of fractals in nature and in our body. So let me come to the conclusions. I have been telling you about how to construct an electronic quantum fractal, an electronic quantum simulator that in the shape of a fractal that could allow us to verify that electrons living in these structures have the fractal dimension. They perceive the fractal dimension. Their wave function can see that they live in a fractal. After that, we went into photonic quantum simulators to understand how is the dynamic of a quantum particle in a fractal. And we have seen that is different from in a classical fractal. Then in the last part, I have shown you how to get topological effects in fractals, and we investigated the real material, which was bismuth grown on indium antimonide, and we could understand all the topological phases that emerge and that we indeed have the best of the two worlds, because we have one-dimensional lines along all these little square triangles, inside and outside, but we also have corner modes that are characteristic of one-dimensional systems. So it is very nice because we got the best of the two worlds. And finally, I have shown you just a one page of a theoretical model that we proposed how to construct fractal Fermi surfaces, and the results that we obtained by the fractal lattice Hubbard model. So I would like to conclude by acknowledging all the wonderful people with whom I have the pleasure to collaborate and supervise. Sander Kempkes and Marlu Slot did the electronic fractal. Xiaoyun Shu did the photonic fractal. Shen Liu, Robert, Rodrigo, and Lumen for the last fractal, the bismuthine on indium antimonide. Malte, Monica, and Vinicius for the fractal Hubbard model. And these nice people down here, and there are two from Colombia and three Dutch. They are also my PhD students. Zeb is a bachelor thesis student. The other four in Lumen are PhD students, and they are doing other very cool stuff that I didn't get the occasion to tell you today, like fractional calculus and solving systems coupled, fractionally coupled to Bath, or systems, interacting systems. Anwar is doing the interacting SSH model, or systems protected by latent symmetries that started by Malte. So with this, I would like to thank you very much for your attention and offer you some flowers, some fractal flowers.